Okay, ladies and gentlemen, let's continue after our previous lecture on the lumped system, which is still part of chapter 4 of transient heat transfer in the textbook of Cengel and Ghajar. We have looked at two examples where we applied the lumped system approach. The one was a sphere made from stainless steel, and the other one was a beer. Okay, the beer was at 40 degrees Celsius, and we wanted to know how long is it going to take to get it to 10 degrees Celsius. And we did some calculations. But the question is, can we believe it? Is it going to be accurate? The other example was the sphere. It was at 150 degrees Celsius in an oven. Then we take it out, and the question was, how long will it be? How long will it take before it would be at a temperature of 50 degrees Celsius so that we can pick it up? We've done the calculations, and then we said that we need a logical, simple criteria to guide us and to help us so that we can decide when we can use the Biot number, or when we can use this criteria, or when we can use the lump system approach, sorry. And this criteria is the Biot number. And the Biot number is the heat transfer coefficient multiplied by characteristic length divided by the thermal conductivity, and the characteristic length is calculated as the volume divided by the area. So for the sphere, we have these volumes and areas. We've calculated the characteristic length. We've calculated the Biot number, which was orders of magnitude smaller than 0.1. So according to this criteria, we can definitely use the lump system approach, and it would give us a good result. The beer, on the other hand, gave us 0.2, which is now just outside this magic number of 0.1. So apparently it seems now as if we cannot use the lump system approach to make an estimate of how long it will take for the beer to get to 10 degrees Celsius. Right. Now I would like to zoom in on this Biot number, what it actually means, and specifically that criteria. So if you've divided your page in two, I would like to continue on this side with a sphere. Okay. So if I continue specifically with a sphere, let's just see what is happening here. With a sphere, in terms of heat transfer, where was the temperature on the outside, and that is now the temperature that changes as function of time, the heat transfer would be from the higher temperature to the lower temperature. In this case, that was the higher temperature, so the heat transfer would be in that direction. That is the resistance of the convection, and that is the resistance of the conduction. Okay. So let's go and calculate these resistances. The first one, the one of conduction. The one of conduction typically is LC divided by Ka for a plane wall. And there are different ones for different geometries. Okay. So I'm going to use this one just now because you're going to see later on why and where it comes from. So I've got the characteristic length, which is 0.001667 divided by the thermal conductivity of the stainless steel. It was 429 divided by A. Okay. So the result, the conduction resistance, is approximately 3.85 multiplied by 10 to the minus 6 divided by the surface area. Now let's calculate the resistance of the convection. The convection resistance is 1 divided by the heat transfer coefficient multiplied by the area. The heat transfer coefficient was 12, so it is 1 divided by 12 multiplied by the area. And that would be equal to 8.33 multiplied by 10 to the minus 2 divided by the area. Right, now the surface area is the same for both the resistances. Okay, of course, we're talking of the same surface area. So if we now look at these two resistance terms, then, and we want to put values on them, then that one would be 3.85 multiplied by 10 to the minus 6, and this one would be 8.33 multiplied by 10 to the minus 2. Very easy to do the calculations, and there they are. But what this is all about, and with many of the problems in heat transfer, is that you shouldn't just do the calculations. Your judgment in terms of looking at the values and getting a physical understanding of what is happening is in most cases more important than the detailed calculations. Okay. So what we have here is, if we now look at the two values of the resistance terms, they are orders of magnitude different from each other. You see that? Okay. So, I mean, if we would now look at this value, the convection value, the resistance of convection divided by the resistance of conduction, then that ratio is 21,405. Right, so if I would now like to go and draw it on scale, okay, it would mean that, okay, there's the first resistance, 1 millimeter, okay, of the conduction. Now the one for the convection. If that is 1 millimeter, how long must this one be? 21 meters. Okay. You understand? Okay. So we're talking of 1 to about 21 in ratio. So the convection resistance is 21 times more than that of the conduction. So that is the hamburgers coming into the venue. Okay, if you're all hungry, after a few days, I only give you water, and we get hamburgers coming in there. Okay. The resistance of the hamburgers getting in here is one issue, but the moment it's going to start appearing in here, it's going to disappear like that. So there's going to be no gradient on the inside. There's no resistance almost for the heat transfer. All the resistance actually lies here. Okay. You understand? Right. So with a beer, it is the other way around. Okay, now I'm continuing on the second column, on that side. Okay, so again, if we now do the same thing for the beer, then this resistance is 0.01597, and this one is equal to 0.0833. And it would mean that the ratio of the convection to conduction is equal to 5.2. Okay, 5 times more. So again, if I would draw it on scale, okay, if that is now 1 unit there, then that is what's going to happen. Okay. So again, this resistance is much larger than that one. So this Biot number of 0.1, what does it actually mean? It means that, okay, so now I'm finished with the two columns. You can put them together again. Okay, so the Biot number, this ratio of smaller than 0.1, it means that if that resistance is 1 and this one 10, then the Biot number would start giving you, or the lump system approach would give good answers. That is what it means. So this is an arbitrary choice. It's 10 times more. That is where it comes from. 1 divided by 10, 0.1. You might have chosen something different. And that is very important to understand. Okay. So it all depends on your circumstances, how accurate you want the results. Okay. So in terms of the example of the beer, where you have chosen a temperature of 10 degrees Celsius, a Biot number of 0.2, doesn't mean the answer is going to be that bad. It's not going to be accurate, but it would be okay, depending on how accurate you want. So again, in design applications, if you're in an application where it's a critical part of a nuclear reactor, then it would be very, very important. Okay. Or in aerospace. But in a mining application maybe, where you work with labor which are not well trained, in many cases equipment are not that, I wouldn't say well designed, but they are designed much more robust than others. Okay. Many people would say that, you know, in mining engineering, it is a cowboy type of design. You know, everything is, you design it and make it thicker and stuff like that. You try to make everything thicker and stronger. Lots of safety factors. So it depends on the circumstances, and you always have to use your judgment, and that is very important. So do not think that the Biot number of 0.1 is the alpha and the omega. It's important guideline, but it's for you to choose one day. Right. Now in terms of, let's call it the formal derivation of the Biot number. Now that we know that, the Biot number is therefore the ratio of convection heat transfer to conduction heat transfer. Okay, so the ratio of convection to conduction. Okay, now convection, or heat transfer in general, we've said is equal to delta T divided by a resistance. Okay. So for convection heat transfer, we would say it is delta T divided by the resistance for convection. Are you happy with that? Okay. While with conduction, it would again be delta T divided by the resistance for conduction. You can see the two delta T's disappear. Okay. And or you can write it as the heat transfer coefficient multiplied by delta T for the convection, and for the conduction you can write it as K divided by LC multiplied by delta T. Again, those would disappear, and the result is that the Biot number, depending how you want to use it, is actually the ratio of the resistance of the conduction to convection. Okay, so it is this resistance divided by that resistance. That is the Biot number, or as we've done previously, is equal to H multiplied by LC divided by K. So, in terms of general guidelines, okay. Again, remember, it's a guideline. So the lump system approach, typically, the Biot number smaller than 0.1. In the textbook, it says equal to, I would rather prefer to say approximately smaller than 0.1. That would be the first thing that should guide you. Then other things that should guide you would be how do we get this ratio small if the dimensions are small? Okay, so small dimensions, okay, would help. High thermal conductivity would help. And what else would help? The heat transfer coefficient. If the heat transfer coefficient is environments in which the heat transfer coefficient is low. Some of you, somebody mentioned yesterday in terms of getting the beer cold, putting it in water. Now putting it in water is going to increase the heat transfer coefficient with an order of magnitude. But the Biot number now suddenly is also going to increase with an order of magnitude. So yes, your estimate of using the lump system approach wouldn't be accurate, but in general, it would still be a good guideline. Right, now something that is very, very difficult for students to follow is something which is stated in the textbook, and I would like to zoom in on that. If we now look at different geometries, and on this side I would say lump systems, and on this side other geometries. Okay. Now for the plane wall case would be something like that. Okay. And that would be equal to 2L. Okay. And the characteristic length would be equal to L. Okay. Most students don't have a problem with that. Okay. Now what do we mean with a plane wall? With a plane wall, we would mean that the heat transfer rate would be in one dimension. Plane wall would mean this wall is very, very long. So if we take this dimension L, not L, let's rather use Z. Okay. So Z, in many cases, many people would say, should be about 10 times more than that. Okay. Again, it is just a judgment. But in principle, this type of problem is going to give us very, very good answers the longer it is. Why? Because then the heat transfer through here is going to be much, much smaller than the heat transfer through the sides. Okay. So in general, it is sort of the same, it would become the same as if that would be insulated. All the heat transfer is in one dimension from the side. And for such a case, the characteristic length would be equal to L. Now, if you look at this definition, you would wonder, well, where does it come from? And I'm going to show it to you just now. Then the next one is the long cylinder. Now the long cylinder looks like this. And again, this cylinder, the longer the better. Let's call that dimension Z. And then the last one is the sphere. Okay. Now with this one, we use that radius as R0. And with the sphere, this one is R0. Okay. Now in the textbook, it says under equation 4.9. Under equation 4.9, there's a paragraph that always confuses students. So go and mark it in your textbook and say very, very important and refer to this because I'm going to clarify it to you. Okay. In it, it says that the characteristic length for plane wall is L, and then it is equal to R0 divided by 2 and R0 divided by 3. Okay. That is not a general statement. So many students use this and then they're going to use it in the next part of the chapter. And then nothing is going to work. So it's very, very important that you keep it separate. Okay. So in terms of the rest of the textbook, it's actually going to work out for the same geometry. The characteristic length later on is going to be L. For a long cylinder, it is going to be the radius. And for a sphere, it is also going to be a radius. Now where does this come from? Okay. Where does this come from? Okay. Maybe the author should maybe have just put in another paragraph and made it very, very clear that that paragraph under equation 4.9 is only valid for the lumped system approach. So where does that come from? It comes from the definition of the characteristic length, which is the volume divided by the area. Let's choose, for example, the long cylinder as just an example. Okay. Right, so the volume would be equal to pi divided by 4 multiplied by d squared multiplied by z. Let's just choose a value of z. Okay? That would be the volume. That's correct. Divided by the surface area. And the surface area would be pi multiplied by the diameter multiplied by L, z. Okay? The z's cancel, the pi cancel, one of the d's disappear, and we end up with, I'm sorry, I have to go on here, and we end up with d divided by 4. You agree? The diameter is equal to 2 times the radius divided by 4, and it's equal to R0 divided by 2. So that is where it comes from. Okay. So it is just from the calculations of that ratio. Text 9. Characteristic length, volume divided by the area. The volume for the long cylinder, pi divided by 4 multiplied by diameter, square multiplied by z. Surface area, pi multiplied by the diameter multiplied by z. The z's disappear, the pi's also, we end up with diameter divided by 4. The diameter is 2 times the radius divided by 4, or 0 divided by 3. So, for this one, exactly the same. Okay. So that characteristic length is equal again to the volume divided by the area. The volume of a sphere is pi divided by 6 multiplied by d to the third, divided by the area of a sphere, which is pi d squared. Okay. And the result is the diameter divided by 6. The diameter is 2 times the radius divided by 6, and it is R0 divided by 3. You can go do the same with a plain wall. Just choose a distance Z, and you're going to get the same value. So that paragraph, very, very important, is only applicable to lumped system. You can't use it for the rest of the chapter. Okay. How are we doing with the time?
Giving me a warning.
Is it giving you a warning? Okay. Ladies and gentlemen, thank you very much. We're going to end the lecture here. If you can just cut it for us.